Salmon farming in Norway generates billions of euros annually and has grown into one of Norway's biggest export industries. The value of a single salmon has on occasion surpassed that of a barrel of oil. But salmon are carnivores by nature, and fish oil and fish meal have become scarce resources in producing fish feed. Thus, sustainable growth in salmon farming requires salmon to eat stuff it isn't evolved for. Through years of trial and error, researchers have developed feeds made from 75% plants, such as soybeans. But this has not been easy, as soy by itself causes inflammation of the gut. Today, this problem is alleviated by feed processing and additives. But getting there took a lot of time, money, and struggle. And still, it isn't particularly sustainable, for the soy fields could instead have produced food for humans. Researchers are now trialling feeds derived from grass, sawdust, and seaweed, resources unfit for human consumption. These novel feeds pose new challenges for the salmon body. Can we solve them quicker this time? Can we compute how to compose a feed that is good for fish, folk, and for business? Systems biology addresses complex interplays in biological systems. The Digital Salmon Research Program aims to build a collection of mathematical models of the life processes in the salmon body, such as metabolism. Based on how salmon breaks down feed ingredients and converts them to fish meat and bodily waste, we compose a model to compute likely outcomes of feeding various possible diets to salmon. If salmon is fed yeast instead of fish meal, will it require vitamin supplements? Could novel feed ingredients cause inflammation? If so, how can we prevent this? To tackle these questions mathematically, we must describe the actors in the system, such as feedstuffs, cells, hormones, and the organs of the body, and the processes, such as breakdown of feed and building of muscle, or triggering of inflammatory hormones by certain substances. The model will shed light on how a multitude of potential diets may affect the salmon body and point to factors that may mitigate inflammation or improve feed utilization. The grand aim of this digitalization of the salmon body is to accumulate a library of various models of life processes in the body, to quickly construct suit-tailored computer simulations to compute effective use of resources, for food security, fish welfare, and human health. Such a digital salmon knowledge base will enable faster response to new challenges such as climate change, new diseases, or scarcity of key feedstuffs. In the future, fish farms will stream data to the digital salmon, making aquaculture more adaptable and sustainable.